So today we want to talk about Einstein's field equations for gravitation, because we essentially have all those. So energy momentum tensor was done yesterday. Okay, so I take that as given. Yeah, it's going to sit on the right hand side of Einstein equations. Right. So the question for us is how to construct Einstein's equations from the Riemann tensor. So we have convinced ourselves that Einstein's equations should describe curvature of space-time as produced by matter. Curvature is described by the Riemann tensor. So this is something about relating something made from the Riemann tensor to the energy momentum tensor. Now we can just write down Einstein field equations if we want. We cannot derive field equations. The field equations are always written down, guessed, and then compared with experiment. But we can motivate it, trying to follow Einstein's reasoning. So for now we assume, is there anything on the chat? We will assume that torsion is 0. The connection is metric compatible. That is, gammas are symmetric and written in terms of the metric. So it's the Levi-Civita connection. We seek to generalize the Poisson equation of Newtonian gravitation and replace it by second order in derivatives equation for the 10 metric components of G mu nu. The metric G mu nu is the gravitational potential. Why second order in metric derivative? That is an assumption. It is not some rigid requirement. We assume, because here also it's second derivatives. You have second derivatives of the potential. We want second derivatives of the metric G mu nu, because the metric 10 components are now going to be like the potential. But it can't be the Laplacian, because the Laplacian is not Lorentz invariant. Locally, whatever is there should be Lorentz invariant. So at least here we need a D'Alembertian, at least. The source is the energy momentum tensor, which is symmetric. In general relativity, it is symmetric. It is the current of current, meaning the latter, which current we are talking of? As we said, mass density cannot be used directly. Mass is part of the energy momentum 4 vector, and so first we have to have an energy momentum 4 vector here and its current. By current of current, it means it will give us something like energy density, flow of energy, pressure, etc. Okay? So we seek field equations of the type some operator acting on the metric should be some constant times T mu nu. These equations should reduce to the Poisson equation in the non-relativistic limit for weak fields and slowly moving sources. What is meant by weak fields? The potential has to be small. It has to be first written in dimensionless units. Potential has dimensions of c square, square of the speed of light. Phi by c square should be much less than 1. When phi by c square is much less than 1, G mu nu should reduce to phi. The 10 components should reduce to just 1 component. The energy momentum tensor should just reduce to the mass density. That is a demand on whatever final Einstein equations we are looking for. Expect this constant of proportionality, expect this constant to be proportional to the gravitational constant G, Newton's gravity. Why? Because G is there on the right hand side, so expect G to be there in this constant also. Now what about dimensions? Let's look at dimensions. Metric is dimensionless. Yeah? Metric derivatives are 1 over length, metric second derivatives are 1 over length square. Curvature has dimensions of 1 over length square, okay, because second derivatives are metric. Irrespective of the number of dimensions of your space or space-time, even in a 10-dimensional space-time, curvature has dimension of 1 over length square. Okay, that's why somebody asked, is you calculated surfaces? I think you were asking. So the components of the Riemann tensor are always calculated on surfaces, 2D surfaces, even in a higher dimensional space. We anticipate the operator to have dimensions of 1 over length square, right? Because it is made from the Riemann tensor. Operator here should have dimensions of 1 over length square, same as the Laplacian. The Laplacian also has dimensions of 1 over length square. Okay? The Riemann tensor has dimensions of 1 over length square. Energy momentum tensor has dimensions of energy over length cube. Yeah? This is energy density, right? So it has energy over length cube. So T mu nu is energy over length cube. G mu nu is dimensionless. This operator is 1 over length square. So what are the dimensions of this constant? It should be a length over energy, right? Because this is energy over length cube into length over energy. Energy cancelled, this would give you 1 over length square. Yeah. So the energy momentum tensor has, so this constant has dimensions of energy over length, length over energy. This constant should be length over energy, so that energy cancels. Length over length cube gives me 1 over length square. Now if you want a constant of length over energy, which should be proportional to Newton's gravitational constant, this is the only other possibility. You have to divide by the 4th power of speed. And what is the natural fundamental constant of speed? It is speed of light. Yeah? So you can anticipate what this constant is going to be. It's going to be g over c4. The Riemann tensor involves first and second derivatives of the metric, and it is linear in the second derivatives. Okay, this is we can just see it. Only first and second derivatives of the metric are there, and it is linear in the second derivatives. Let us see that. This is my expression for the Riemann tensor, which you have seen many times. Is proportional to derivatives of gamma and or terms which are gamma gamma. This is the Riemann tensor, irrespective of the metric. But suppose you say I have 0 torsion and it is metric compatible, then the Christoffel symbols are symmetric. They are the Levi-Civita connection written in terms of the metric like this. Just substitute this expression for gamma in the expression for the Riemann tensor. You get this long expression for the Riemann tensor in metric components. So we don't have to look at each term. Just see, these are the terms which are second derivative in the metric. It's linear in those terms. Then there are terms which are first derivatives of the metric. It is bilinear in those terms. Yeah, this is all we need to know from here. This g by itself has come just because I've raised one index. You lower that index, this metric will go away. So it's clear from here that what you have is derivatives, first derivatives of the metric here, second derivatives of the metric here, bilinear in the first derivatives of the metric from here. It's very clear. That's what's happening. So I have to make a second rank tensor from this, which is sitting on the left hand side. And if I make it from the Riemann tensor, it is going to be linear in the second derivative of the metric. Yes, and this is good. This is like the Laplacian, right? G's are potentials. These are second derivatives of g. This is like the, it has the same overall picture as the Laplacian. Okay? Alright, let's proceed. Demand that the Einstein equations be linear in the second derivative. This is the demand, and if the left hand side is to be made from the Riemann tensor, it will naturally come about. So the desired field equations are of the type: a second rank tensor made from the Riemann tensor. The coupling constant is g by c4 times some number. It won't have to be g by c4. will be some numerical constant times g by 4 into t mu nu. Going further, the left hand side is a symmetric second rank tensor made from the Riemann tensor. Symmetric because the right hand side is symmetric. The number A is to be obtained by demanding that in the limit of weak fields and slow moving sources, these field equations reduce to the Poisson equation for Newtonian gravitation. This should become Laplacian phi equals 4 pi 0. The C4 will cancel, but if you want to get 4 pi, you will have to put a suitable A here. Yeah? The second rank tensor on the left hand side must have vanishing divergence. Why? Because the energy momentum tensor has to be conserved. T mu nu covariant derivative nu is 0. So whatever second rank tensor you put on the left hand side, it should have 0 divergence. Now, what second rank tensor can it be? The only second rank tensor one can make from the Riemann tensor is the Ricci tensor. This is the Ricci tensor. You contract the first and the third index. If you instead choose to contract first and the fourth index, you will just have a sign change because it is antisymmetric in the second pair. And if you contract the first and the second index, you will get 0 because it is antisymmetric in the first pair. So you can convince yourself that there is only one way to get a second rank tensor by just contracting the Riemann tensor. This is the Ricci tensor. It is symmetric. You can check that. And it has hence 10 independent components. Riemann has 20, Ricci has 10. So clearly the Ricci tensor is not carrying all the information of Riemann. The rest is carried by the Weyl tensor. We will come to that in a moment. However, the Ricci tensor does not have 0 divergence. It does not obey the Bianchi identity. What has 0 divergence? From the Ricci tensor, one can make the Ricci scalar, contract these two indices also. You have only R, the Ricci scalar. Define the Einstein tensor as Ricci minus half Gij R. This fellow we know has 0 divergence. It follows from the Bianchi identity. You can check explicitly also that the Einstein tensor has 0 divergence. It is a good candidate to be put on the left hand side of Einstein equation. Yeah? Any questions? Okay. So let's proceed. So hence, we know what should be on the left hand side, and we can, so we have the Einstein equations. What did we do for that numerical constant A? It has been fixed by demanding that in the weak field non-relativistic limit, you write down the a general metric in the Einstein equations with G00, G0I, Z alpha beta. You can check that if you have, what will you put for T mu nu? Slow moving, non-relativistic. There is only one component, T00, the energy density. Yeah? Because also that's what should come in the Poisson equation. And in that limit, the metric has only one non-zero dominant component, that is G00, which I define a potential phi from G00 using this equation with 2 phi by c square much less than 1. If you take G00 like this, put the other components of G to be 0, substitute it on the left hand side. We know these are all functions of the metric. We know how to compute them. So just plug it in. The left hand side will become Laplacian of phi, and right hand side will be just 4 pi 0. What happened to the C4 factor? The 1 by c square coming from the left hand side will cancel by 1 by c square, and the other c square will convert energy density to mass density. E equals mc square, so m is E by c square. So by demanding that these equations reduce to this in the non-relativistic weak field limit, we can fix A to be 8 pi. So this is essentially 8 pi divided by 2 will give me 4 pi. So we have fixed Einstein equations. Still we don't know. I mean, yes, I have done some logic and but how does Einstein know this is correct? So it is not pure thought. He has to check it against data. He had one good data point right away. He calculated the orbit of Mercury from here. It produces a correction to the Newtonian gravitation. The orbit is not merely an ellipse. It rotates, it precesses. That precession, as you know, it was worked out in the class. Ashmita did it on first day. That precession of the orbit is 43 seconds of arc per century. And the correction to the Newtonian gravitation 1 by r square law coming from here was used by Einstein to predict, to calculate that precession, and to get the exact number is a great achievement. Even a great man like Einstein was besides himself his joy. So he used this phrase, he saw God. You know, if your number produces what you are seeing, if your equations produce that, you are sort of talking, your equations are talking to God. There is no reason why it could have been 25 instead of 43, to be exact. So that gave him great confidence. So that is what we call a post-diction. He did not predict the precession, he post-dicted. It was already there, he explained it, and as you know, until then there was also considered a possibility that between Sun and Mercury there is another planet. What's it called? Vulcan. It was a name given to it. A hypothetical planet which was perturbing, supposedly perturbing Mercury's orbit, and you could place the planet such a way that you get 43 seconds of arc. So that is like a Ptolemy epicycle of a kind. So there was a competition between these two ideas. Is there dark matter? Vulcan is the dark matter. Or is there modified gravity? Is Newton's law of gravitation breaking down for Mercury's orbit? Or is it there unseen dark matter like the hidden unseen planet? So this time modified gravity won. So Einstein gravity is modified gravity from those days. Nowadays Einstein gravity is the standard and we are trying to modify it. And for galaxy rotation curves, we don't know whether it's modified gravity or dark matter. Dark matter is more popular, but maybe it is still modified gravity. Once again, you have to change Einstein's law of gravitation. We don't know, only data and time and further research will tell. Great. Any questions?
It's not modified in the same way.
Namely?
It's not modified in the same way. These are not equivalent.
General relativity is not modified Newtonian gravity.
Not in the same way we are modifying PR to...
I don't agree. Mond may not look as pretty as GR, I agree. But we are looking for a theory underlying Mond, presumably as beautiful as general relativity.
Oh, okay.
In that sense. Mond is phenomenology, I agree with you. But we are looking for something which is as pretty as general relativity, but it is not general. That's why I said in the first lecture, sorry?
More from basic principles.
Yes. That's what I talked of in my seminar, the so-called dark electromagnetism. That's one example. So what is happening there is, just since you asked, I'm tempted. Electroweak is SU2 cross U1. GR is like SU2. The U1 we are proposing is like electromagnetism. So SU2 cross UR, GR cross dark electromagnetism. Inside, if it is true, it's pretty. We don't know if it's true. So how do we know this is a relativistic theory, this one? Because in a freely falling frame, the metric locally reduces to the Minkowski metric, right? That is the reason why this is a relativistic theory. And as we said yesterday, Newtonian gravity can also be described as curvature, because this is just a special case of these equations where space-time geometry is interpreted as curvature. So this is also curvature. Newtonian gravity is also curvature. The Earth's path around the Sun is quote-unquote a straight line. It's a straight line in a new geometry, the Schwarzschild geometry produced by the Sun. So we don't call it straight line, call it geodesics, but that's essentially what's happening. The straight line, the so-called straight line, is not a straight line in the Euclidean sense, it is a straight line in a curved space. If the requirement of the Newtonian limit is relaxed, one can include the cosmological constant. You can add one more term which is proportional to the metric. This will still have zero divergence on the left hand side because the covariant derivative of the metric is zero. So that condition is satisfied, the covariant divergence of the left hand side vanishes. But now in the Newtonian limit you will have a term like lambda, some constant term due to lambda will come about, but that lambda is strongly constrained in the solar system because it should not perturb planetary orbits. So that lambda value, I think, is, I don't remember, MTW has a problem, of the same order as the currently suggested lambda in cosmology. Question? Any question? Why add cosmological term lambda? Very good question. Okay, as you know, there is a history. The cosmological constant was first added by lambda because he got worried by Einstein. Cosmological constant was added by Einstein because when he wrote these equations and applied it to cosmology, he wanted to get a static universe, because that's what you saw, right? I said in my first lecture, there is no sign of an expanding universe when you look up in the sky, it's static. So the belief system in 1915 was the universe is static. We did not even know whether there are galaxies outside the Milky Way. Those so-called nebulae were thought to be in the Milky Way. Even extragalactic galaxies outside our galaxy had not been discovered, let alone expansion. Then, so the universe was static. These equations predicted an expanding universe. So with that got Einstein worried. So again, another evidence that is not pure thought. He was trying to fit the theory to data. Pure thought would have meant he would have predicted expansion of the universe, and that would be great. Einstein himself regretted it. So to get a static universe to overcome the expanding universe prediction, he added a cosmological constant to get a static solution. Then in 1929, when Hubble discovered the expansion universe and also showed that these galaxies are out, the so-called nebulae are outside our galaxy. They are independent galaxies in their own right. They are moving away from us, so the universe is expanding. So then lambda was dropped, yeah, because then you want the expanding universe solution. But lambda can do other things. Lambda can make an expanding universe accelerate. Normal expanding universe without lambda will slow down. It's the same thing as you throw a stone up, it slows down, falls back to earth. So expanding universe obeying these Einstein equations will slow down. It will recollapse or keep on expanding, but it will be slowing down. But when in 1999 astronomers claimed to have discovered that the expansion was not slowing down but speeding up, accelerating, lambda was brought in as one possible explanation for it. So not only can it produce a static universe, it can also produce, depending on your basic assumptions, it can produce acceleration also. So this is what should I call it, the various reincarnations of the cosmological constant. Brought in, removed, brought back, maybe still removed, we don't know. because there are people like Subir Sarkar saying and his group saying that maybe the expansion is due to the fact that the universe after all may not be homogeneous and isotropic, and some inhomogeneities are causing an illusion of acceleration. Okay. Questions?
Yeah, quick question. So the first equation doesn't necessarily apply only for a static universe, right? It can allow for a steady expansion or contraction. Only the accelerated expansion is what makes us into.
Yes, if you want acceleration, you will not get it from that equation. You are absolutely right. Then you have to have not necessarily lambda, something which will do what we call, the condition is that you need negative pressures. Rho plus 3p, where rho is the energy density, p is the pressure, rho plus 3p should be negative. If you are in a homogeneous and isotropic universe, scale factor measures the expansion. If the expansion has to accelerate, rho plus 3p should be negative. Lambda is one case which gives you negative pressures, p equals minus rho, so rho plus 3p is negative. You can do it other ways of question. GR is a fundamental theory, but unfortunately it is not part of the curriculum. I will talk about this in the end. We can discuss it later, please. Okay. In the matter-free region, Ricci tensor and Ricci scalar are both 0. So suppose you put T mu nu here, not lambda, forget lambda for now. If you put T mu nu as 0, the left hand side is 0, make a contraction. Rij contracted will become R, Gij contracted is 4, delta function. 4 by 2, 2, so R is 0. If T mu nu is 0, then the Ricci scalar is 0. If the Ricci scalar is 0, Rij is 0. So in free space, the Ricci tensor and Ricci scalar both vanish. Such solutions are called Ricci flat. And what about curvature? Who describes curvature? If you are outside the sun, outside is vacuum. There is no matter. Outside the sun, there is no matter. T mu nu is 0. So R is 0, Rij is 0. R and Rij is 0 only in the sun, inside the sun, where there is matter. No matter, Rij, if there is no matter, Rij and R are 0. But still there is a gravitational field, no? The earth feels the gravitational field of the sun, despite the Ricci tensor and Ricci scalar vanish. It means that information about curvature is carried by some other component of the Riemann that we already saw. The Riemann tensor has 20 components, Ricci has 10. There are 10 more, that's the Weyl tensor. The additional 10 do not vanish in empty space-time. In the matter-free region, curvature comes from the Weyl tensor. The Riemann tensor has 20 components, Ricci has only 10. The remaining information about curvature comes from the Weyl tensor, defined like this. Riemann equals Weyl plus a part, n is the number of space-time dimensions, so 4 for us, put 4 in this expression. This part you can see is made only from Ricci tensor and Ricci scalar. These square brackets denote anti-symmetrization. The Weyl tensor is the totally trace-free part of the Riemann tensor. What does that mean? So it is what remains when Ricci tensor and Ricci scalar have been subtracted out from Riemann. So, and I spent some time answering Rajesh's questions, your question about interpreting Ricci and all. So we do that now. So if suppose you take a trace of Riemann, you will get Ricci, you will get one more trace, you get Ricci scalar. Whatever is left is totally traceless, meaning this Weyl tensor C, take a trace, so put this row up, take a trace of rho with any of the other 3 indices, that trace will be 0. So the Weyl tensor is the traceless, totally traceless part of the Riemann tensor. The Weyl measures geodesic deviation in empty space. So in empty space, all these second and third term are 0. Riemann is equal to the Weyl. So now I explain. So what does Ricci do and what does Weyl do? They are both curvatures, but they have different physical interpretation, different physical consequences. So what is that? I explain in a few lines. The Ricci part measures how volumes contract or expand. This can be proved mathematically. So let's say you have a ball of particles. Think of a sphere. There are particles inside it. This ball, all the particles are moving along geodesics. You're given some gravitational field. This ball is falling in the gravitational field. What does curvature do? It will distort the ball in various ways. What can it do? It can shrink or expand it. That's a change of volume. Or tidal forces, it can stretch it and squeeze. This sphere may become an ellipsoid. Squeezed in one direction, stretched in the other, that's called shear. Or vorticity, it can rotate. What you are doing here is take the force velocity of any one particle u mu, take its gradient, grad mu u nu. This is a velocity gradient tensor. It's well known in fluid mechanics that this can be decomposed into three parts called the expansion, shear, and vorticity. Expansion is a scalar. The shear is a symmetric second rank tensor, the shear tensor. Vorticity, which measures rotation, is a second rank antisymmetric tensor. The shear tensor is also traceless. Shear tensor is symmetric and traceless. Its trace part is theta and vorticity is antisymmetric. So, starting from the geodesic deviation equation applied to a ball of particles which has some volume theta, you can write this famous Ricci equation. Yeah, this is the Ricci equation. It tells you how expansions, the volume, theta is the expansion scalar. It measures how the volume of that ball is changing. It's given by this equation. Notice that it has only Ricci tensor in it. It does not have Weyl in it. Yeah? Showing that the expansion couples to the Ricci tensor. What the Ricci does, you take a ball, its volume change are determined by the Ricci. Now clearly Ricci is 0 in empty space, so no volume change if you are in empty space. The ball has to be inside matter for its volume to change. And what happens outside in empty space, in vacuum? There is Weyl curvature. So correspondingly you have equations for the shear and the vorticity. I did not write them down here. Just as there is the equation for the evolution of the expansion, the volume of the ball. So this equation, famous equation, the best work in relativity to come out of India all times, Ricci equation, 1953, to be later used by Penrose and Hawking in the proof of singularity theorems, for which Penrose got the Nobel Prize. So there is a lot of Ricci in that Nobel Prize. Yeah. So subsequently others wrote corresponding equations for the shear and vorticity evolution. But that was all motivated by Ricci's discovery. I think already he was at Presidency College. It was Presidency College there in 53. It was there, so he was there, I think, and stayed there always. Ashutosh, okay. Presidency is not started yet, is it? Is the college still there? Okay. But Presidency become more famous. Okay. Thank you. Okay. Thanks for that update. In vacuum, there is Weyl curvature. The Weyl curvature, it turns out, can be split into so-called electric and magnetic paths which have analogies with electromagnetism. The Weyl curvature enters the evolution equation for shear, which causes stretching and squeezing. In the vorticity equation, curvature does not enter directly. Gravity does not generate vorticity from zero, whereas gravity will generate shear from zero. The shear is basically tidal forces. The tidal forces are caused by the Weyl curvature. Okay, questions? Yeah, I will not go into it now. Good question. It's a decomposition of the Weyl tensor into the magnetic part and the electric. It does something very interesting things. Today we will not go into. Yeah. Okay, so now this very interesting question. I talked to Rajesh, I think to Parisi also. Do the Einstein equations determine the Weyl tensor? It's a very interesting question. We can discuss it for some time. Because see, through matter, Einstein equations determining only the Ricci. So when we say gravity is the curvature of space-time, what happened to the other half? So we can debate this. Not entirely. Do Einstein equations determine Weyl? Not entirely. The free gravitational fields such as gravitational waves have a non-zero Weyl, but this is not coming directly from the Einstein equations. These equations determine Weyl through the metric. Einstein equations solve for the metric. Once you have the metric, you can calculate the Weyl tensor also. That's the gravitational field of the sun outside in vacuum. It is Weyl only. But that is not all of the Weyl tensor. You could have a gravitational wave floating around outside the sun. That will have non-zero Weyl curvature. The matter part there is zero, but gravity is non-zero. It's non-zero Weyl curvature. I'll tell you my way of looking at it. All said and done, gravitational waves do obey the linearized source-free Einstein equations. Box h mean equal to 0. Sanjit might have told you that, yeah? And eventually gravitational waves are in turn produced by accelerating matter itself. So it's not, there's nothing magical. Someday in the past a star was accelerating, quadrupole radiation formula, it gave out gravitational radiation, and that is propagating through space. In that process, Einstein equations were applied. It is the same way as in electrodynamics. Charge density and currents produce electric and magnetic fields, like the Ricci part of Riemann. Yeah? But there are electromagnetic waves too, source-free part. So electromagnetic waves and electromagnetic fields produced by sources. Same way, gravitational waves and gravitational fields produced by matter through RIG. Of course, the analogy with gravitation is not precise because gravitation is producing Weyl also. Weyl is produced by gravitational waves and also by matter. Whereas, so there is a difference from electromagnetic waves. I hope you see that. The Weyl tensor obeys a constraint equation following from the Bianchi identity, which is like this. And in vacuum, where the Ricci tensor is 0, the Weyl tensor obeys this wave equation, constraint on the wave equation. That is like a constraint, say, on gravitational waves. Gravitational waves will have a Weyl, and that Weyl will obey this equation. This is essentially a statement about the tidal forces. Any statement, this is a constraint on the tidal force. The Riemann is a tidal tensor. Why? It's the second derivative of the metric. Like Laplacian phi in Poisson equation, phi is the potential, grad phi is the force. So one more derivative, Laplacian phi is the gradient of the force, which is tides, right? M by r square, m by r cube. So the stretching, what the Riemann tensor is doing is the stretching. That's what the geodesic deviation equation is. It is stretching the distance between geodesics, making it less or more, etc. Yeah, so this is all that I have to say about the Weyl tensors interpretation. Do you have some question now? Because you asked me this good thing. Anything doubt remaining, please ask.
I was wondering, we have this curvature scalar, and in the Einstein equation we only have Ricci tensor, right?
Ricci and Cascade.
Yes. Now, could it be so happen that on the right hand side, of course, we have energy moment tensor. Could it be so happen that there is this a generalized energy moment tensor with 4 indices?
4. Oh.
And this somehow the contracted version appears on this equation.
I would stick with 2, but add an antisymmetric part to T mu nu. That will bring in torsion. The antisymmetric part of T mu nu comes from spin angular momentum, and that will produce torsion. That will have its own Einstein equation, but of course that will still be a Ricci only. But a 4-dimensional T mu nu rho lambda, we have to have an interpretation for it. Maybe yes, but I don't know what is it. It has to have a physical interpretation. Parisi, are you okay? You have questions? You okay? All right, so now next topic. Right, so I now want to tell you a few things about the Riemann tensor and Einstein equations. The Riemann has 20 independent components, but these are all coordinate dependent, right? R, I, J, K, L will be different if you make coordinate transformation. So we want to make scalars, which are coordinate independent invariant scalars. So for example, this is the Riemann scalar, Rijkl upper, Rijkl lower, or the Ricci square, Ricci squared, Rik. Ricci squared is different from the Ricci scalar. Do you understand? Ricci scalar is Rik Gik. It is second order in the metric derivatives. This will have second order derivatives also only, but fourth times linear, G, right? Because each of them will give bilinear terms in G, or quadratic in the second derivatives. So Ricci scalar is only one of the various scalars you can make from the Riemann tensor. But interestingly, you cannot make 20 scalars, you can only make 14. There is some mathematics there. These scalars obey some differential identities. I don't have expertise on that. But only as recently as 1991 was a proper classification of these 14 so-called algebraically independent scalar invariants of the Riemann tensor. So no derivatives. Now if you take derivatives, there will be more scalars. So what are these? Some examples. These R we are familiar. Using just the Ricci tensor, you can make a scalar, right? Where is the Riemann scalar in all this? Why is that not written? RIKLM, maybe it is one of these. I didn't pay attention. This fellow, no, the so-called Riemann scalar. So that might be this. It might be coming from some combination. Write Riemann as Ricci plus Weyl, and then make a scalar from that. I am sorry, I did not pay attention. I'll check it out. The Riemann must be getting made from some combination of these. So these are made only from Ricci and mixed. Ricci times Weyl, and Weyl and mixed. That's what he is calling that. So this is some mathematically rigorous classification. I forget the name of the author's 1991 work. I will try to figure out where is the Riemann scalar in this. Any questions here? No question. Why is there a square in I5? Very good question. So it is not as if, very good question. It's not as if I can take infinitely many higher powers, then I'll keep generating as I take the 4th power, 8th power, there's no end. But this has something to do with what they call algebraic independence. You can make polynomial functions without taking derivatives, and this r mu nu square is in some sense different from the I2. Again, a very good question. I don't think I know the final clear answer, but algebraic independence is there. So that is something like, so I think I have to answer your question better. I'll come back with an answer by tomorrow. I have to think. Very good observation. So the one example is given. Suppose you have a 3 by 3 antisymmetric matrix. There are 6 independent components, but there are only 3 invariants: the trace, the determinant, and the trace of the square. Square the matrix and then take a trace. That is also an invariant, but there are only 3 invariants. So 20 components does not mean 20 invariants. And then I have to answer this question: where is the Kreshman scalar in this, and how is I2 different from I5 despite appearances? So that this is a very, I will figure it out. I don't have an answer right now. All right. So now this is also very interesting. Some important question. Physical signal. Yes. Very good. So let's go back. These invariants carry the same information. These invariants carry the same information essentially as the Riemann tensor components do. If you are measuring a gravitational field and you want to ask what is its strength, is there anything there, please? If you are measuring a gravitational field and you are asking what is its strength, you cannot do that in a coordinate dependent way, because your components will change with coordinates. You want a coordinate independent measure of the strength of the curvature, and that information in a coordinate independent way is captured in these 14. You need all 14 in general if you want to know how much is the strength of the curvature. Yeah? Are these invariants finite at coordinate singularities? Again, excellent question. We have to be very careful whether all invariants. So at coordinate singularities, definitely they will be finite, but at physical singularities, do all diverge? I don't know. Again, very good question. Normally we would check for the divergence, say, of the Kreshman scalar, okay, or in some cases the Ricci scalar, but whether all 14 of them will diverge at a physical singularity, again, is a great question. I don't know the answer. I'll remember it. I'll try to find out. So 3 questions about this table. Where is the Kreshman scalar? Why is I2 and I5 different? And at a curvature, do they all diverge? Is it true that divergence of at least one? No, not at all. Not at all. If one diverges, why should all diverge? That is, they are independent of each other, no? They are independent of each other. So behavior of one need not constrain the behavior of the other. So I will answer this more carefully tomorrow. The divergences of these invariants at singularities, they are useful for also making generalizations of general relativity. For example, if you have you want to start from an new action principle, the action of general relativity involves only the Ricci scalar. You want to make a new theory, so okay, let me make a new theory where the action is, thank you, where the action is r mu nu, r mu nu. I can make a new theory with I2 or with I3 or with I4 or with I1 plus I2 and so on. You can, if you are free to play with the theories as you please. Yeah? Any more questions here? They will follow from here. I cannot take, say for example, r to the 6 and say that that's a different invariant. No.
What was special about R linear to R linear that you could take?
I2 and I5. Yeah, I don't know the answer. I have to check, did I make a typo here? I have to find out. It's a very good question. Why is I2 different from I5? They look the same. I have to figure that out. Is it that the gravity theory with an arbitrary function of I1 R? Yeah, something like that. F of R need not be just, yes, you are right. Anyone F of R, you are F of, who's the F of R person here? Yeah, F of R is some function of R, absolutely. F of R gravity means some arbitrary function of R. Okay. Right, so Einstein equations have some very interesting properties. So we'll discuss that. And the last topic is writing down Einstein's equations and the action principle in the notation of differential geometry.
Actually, I have read some of theories that there is contraction between Ricci and energy momentum.
Oh, yeah, and lot is possible, yes. Yes, so coupling of gravity directly with the energy momentum. Yeah, the world is ours, yes. So as I said, there is no hard and fast rule that gravitational field equations have to be like this. Given, you agree for the equivalence principle that gravity is described by the metric, then it's up to you to write down the action principle and compare it with experiment, absolutely. But there will be resistance because this is beautiful. General relativity is the simplest metric theory. It is beautiful, and then you try to take something beautiful and take the beauty out of it. So as Prakash said, there will be resistance. So F of R can be unpopular also, yeah. Many people don't like F of R. Okay, these are the Einstein equations are 10 second order partial differential equations for the 10 metric components, which are the potentials, to be solved once the energy momentum tensor is prescribed on physical ground. So first you say, what's your source? It has to be something physical, no? What the nature of matter is, Einstein equations will not tell. What is it, a fluid? So that is left to particle physics to tell us what is the fundamental nature of matter. In classical physics, collection of particles, a star, a fluid, etc. What you should not do is what we sometimes jokingly talk of. Take on the left hand side, start with a solution GIK. Say this is my metric. Put it on the left hand side. Calculate Rij minus half Gijr, and then you say this is my Tij. You see the joke there. You have solved Einstein equations for the Tij that came by plugging in a desired metric tensor. That is not a solution, because what is your Tij? What is the kind of, you might be having an absurd Tij. So that's what will not to be done. First say what is your right hand side. Conservation of energy momentum tensor determines the motion of matter fields, but not the equation of state of matter. So to qualify what that means, Tik divergence is 0. Energy momentum is that's a conservation equation, basically saying energy momentum is conserved. Now, when energy momentum is conserved, your equations of motion will follow from there, because it's like, when conservation of kinetic energy plus potential energy, if this is conserved, if you differentiate it, you will get Newton's second law of motion, right? That is quite obvious. But the same kind of thing happens here. Unlike in electrodynamics tells what is the force produced. Force is Q times E plus V cross B. That force you have to put equal to ma, Newton's second law. But here something like f of ma will follow from Einstein equations, except that you cannot predict or derive the properties of matter. So if you have a fluid which has a pressure and it has an energy density, there is a relation between pressure and energy. P equals k rho, for example. That's the equation of state. The equation of state will not come out of Einstein equations, obviously. But once you give the equation of state, the nature of the motion will be determined as a consequence of the covariant divergence of the energy momentum tensor. Because of the freedom of choosing coordinates, 4 out of 10 components of the metric are arbitrary. You see that? I have a G mu nu solution. I have 10 components. You can make 4 coordinate transformations. There is freedom in the choice of 4 of the 10 metric components. So which means the equations should also be a little restrictive, How many Einstein equations are there in 4D? 10. Because G mu nu has 10 components. The capital Gij, the Einstein tensor, that is also 10 components. So there are 10 Einstein equations, but only 6 out of the 10 metric components should be determined by the equations, because 4 are subject to arbitrariness of coordinate transformation. So 10 equations, this way you can look at 10 equations for 6 metric components. And what are the other 3? 3 velocity components. Ui is a 4 velocity, but it has a constraint. Ui equals c square. So 3 velocity components, 6 metric components, and 1 equation of state. So these 10 free parameters for which there are 10 equations. Something very interesting happens. The Einstein equations contain second derivative with respect to time only of the spatial metric components G alpha beta. G mu nu has 10 components. 6 of them are spatial, where alpha and beta go 1, 2, 3. Only time derivatives, I didn't prove this, you can check Landau-Lifshitz classical theory of fields. Second time derivatives only of G alpha beta appear. Question? Second time derivatives of G naught naught and G 0 alpha, where alpha is going from 1, 2, 3. Second derivatives, time derivatives of these 4 fellows do not appear at all. Moreover, these second order time derivatives appear only in the alpha beta equations. You have Gij equals Tij, where Gij is the inner Einstein tensor. Take I up, Gi upper, J lower. So there are 10 such equations. 6 of them you can call spatial equations. The upper index is also spatial, the lower index is also spatial. The second time derivatives appear only in these equations. So second time derivatives only of G alpha beta, and they appear only in these equations. The second time derivatives do not appear in these G00, capital G00 and capital G0 alpha. They don't appear in the second time derivatives, don't appear in these 4 equations. So these latter 4 Einstein equations are constraints. So now what do we expect for field equations? If they are second time derivative equations, that is what we think of as an evolution equation. And suppose that equation has only first time derivatives or no time derivatives. That's like a conservation equation. It's like a kinetic energy plus potential energy is a constant. So 4 out of the 10 Einstein equations are constraint equations. They don't involve second time derivatives. Only 6 equations are dynamical, and these are for the 6 spatial metric components G alpha beta. That's consistent with freedom under coordinate transformations. I'll slow down here. Any questions? So the 10 Einstein equations split into 6 and 4. 6 dynamical, 4 constraints. And this is also very interesting. If the constraints are satisfied at all times, if the 4 constraint equations are satisfied at all times, the dynamical Einstein equations will follow. So either you can write down 10 equations initially and proceed to solve them, or you can say I'll work only with the 4 constraints at all spatial hypersurfaces. Divide space-time into space-like hypersurfaces at different time coordinates. Assume constraints to hold at all the space-like surfaces. Then the other 6 dynamical Einstein equations will follow, which is the reason why in quantum general relativity, one approach to quantizing gravity, like the Ashtekar approach, one works only with the 4 constraint equations. So these are so-called, one is the Hamiltonian constraint, total energy is 0, and 3 are called diffeomorphism constraints, the 4 constraints. And quantization just consists of imposing these constraints on the allowed quantum states. So h equal to 0 and something like pi equal to 0, Hamiltonian constraint and momentum constraint. So if you are allowed quantum state, the way to impose constraint in quantum theory is h psi is 0. The constraint acts on any state to annihilate. The state should obey the constraint. H psi is 0, p psi is 0, this is a Hamiltonian constraint and the momentum constraint. That's all we work with. And the Hamiltonian constraint is also famously known as the Wheeler-Dewitt equation. Maybe you heard of it sometime, yeah, in honor of the people who found it. So the origin of that particular way of quantizing gravity lies in this structure of these equations. What is the initial value problem? How to solve Einstein equation? Specify the initial values of g alpha and g alpha beta dot. Alpha and beta are now spatial. Positions and velocity now become the values of g alpha beta and g alpha beta dot. The constraint equations then determine g00 and g0 alpha, the remaining 4. g0 alpha dot and g00 dot still remain arbitrary. So that is like four coordinate transformations are allowed. So anything you want to ask me here? Okay, so we can move on to the last topic. We want to write down Einstein equations in the differential geometry form, because that's the one path we have followed in the last few lectures. We want to write down the action principle also in a differential geometry notation. So today I think Patrick will derive Einstein equations from the Einstein-Hilbert action. What is that action? Integral d4x r root minus g. This you are familiar with, right? The same action, the Einstein-Hilbert action, integral d4x r root minus g, can be written in the language of curvature 2 forms as follows. So we will work in what is known as the first order or Palatini formalism of GR using, what is the first order formalism? We have the frame field, the Vierbian or the tetrad fields, these are frame 1 forms, the co-frame 1 forms, EA. When did we do that? Yesterday or day before? What did we do yesterday? I forgot. We did 1 forms only, curvature 2 forms, right? Yes, yes. We did curvature 2 forms yesterday. So these are frame forms. These are EAs are the 4 coordinate 1 forms for the coordinate frame. So as I said, one of you had asked, we either call them connection 1 forms or spin connection 1 form, 6 of them in 4D antisymmetric. This is the curvature 2 form, and this is the totally antisymmetric Levi-Civita symbol, which has unit tensor basically. The Einstein-Hilbert action is a function. Right. What is the first order formalism? Independent variations with respect to E and omega. The Einstein-Hilbert action, we vary only with respect to the metric. But there is an equivalent so-called Palatini formalism where you vary with respect to the metric and the connection independently. So this is the equivalent of that in the form language. Vary with respect to E and omega independently. R root minus G looks like this. This I request you to accept. This is the curvature 2 form, RAB, RCD here. Wedge product EB, wedge product EA, contracted ABCD. This is the Ricci scalar actually, nothing but the Ricci question. And this is the matter part. As a function, so some matter field psi, some scalar field or some fluid. This is the matter action. So you have to do two variations. Variations with respect to the co-frame field and variations with respect to the connection, spin connection or connection 1 form. Variation of the gravitational part gives me this delta EA, delta EB. Now there is a variation also on R's on the curvature 2 form. I will not go over into that in detail. Turns out that can be written as a so-called boundary term. Patrick will show that. So if you have the Ricci scalar written as GIK, RIK, you do a variation. There will be a variation on delta GIK times RIK. There will be a variation on GIK times delta RIK. That delta RIK can be converted into a boundary term. So that's why it doesn't show here. The variation of the matter action defines the inner. Can I take this question? Detailed PowerPoint. Oh no. Can we make similar energy? Yes, energy momentum tensor, yeah, but not so many. You can just contract it once. As far as I can, you can make the trace of it. What is this last remark? Detailed PPT, number of concept clear. Do you understand what? Okay, maybe Radhika, you can read.
Complementing the PPTs are detailed and number of concepts are clear.
Okay, thank you. Okay. So we can vary the matter action. This by definition, when you vary the matter Lagrangian, when you vary the matter action with respect to the metric, here with respect to the tetrad, whatever you get is the energy momentum tensor. This Patrick would have done yesterday. So this is the so-called energy momentum 3 form, tau A, just like there is a current 3 form in electrodynamics. You are given the current 1 form, you take its Hodge-star dual, you get a 3 form. So that's the same way, it's like the energy momentum. Okay, the variation of the gravitational part. Right, this we have already written, the variation of the matter action. Somehow this got repeated. And so you can then put these all together, just put the total variation together, set it to 0. So it's much more straightforward here. You combine these two terms and for which vanishes for arbitrary variations, it will just straight away give you the Einstein equations. This can be actually shown to be the Einstein tensor. This is the Einstein equation expressed in differential form, where tau A is related to the standard energy momentum tensor by taking this so-called Hodge-star dual. So this is a 1 form written as a vector valued 1 form. Take its Hodge dual, you will get a 3 form. On the left hand side also there is a 3 form. I think I have a slide working this out. Right. So suppose I claim that these are my Einstein equations. We also wrote that as Gij equals Tij, or Rij minus half Gij equals Tij. So just a simple explanation for how this and the standard form are equivalent to each other. So where did we start? We are here, right? This we have just, maybe I went too fast, but you get some idea. It's not that difficult, how to write the Einstein action in differential form language. The energy momentum 3 form can be written, tau A can be written as TAB times the Hodge dual of this one form EB, where TAB is the energy momentum tensor in the local Lorentz frame and star EB is the Hodge dual of the co-frame. Okay, so where were we? This is my Einstein equation. Again, just skipping some steps, this is a 3 form and it can be written as the Hodge dual of the Einstein tensor. So again, some steps are skipped. This GA is the so-called vector valued one form. GAB is our Einstein tensor, RAB minus half GABR. That if contracted with this EB gives me this so-called one form. Its dual is this 3 form, star GAB. So this is star, this is a star, so 0 factor 2 here. Star GA on the right hand side, was my right hand, what was on the right hand side? The right hand side is 8 pi, no, right hand side is 8 pi tau A. I substitute for tau A, this is where we are, no? Right, I substitute for tau A on the right hand side. That was done here. Write tau A in terms of TAB, write tau A in terms of TAB. This is the left hand side, is the Einstein tensor, both written in duals. Take the dual once again and you will land up with, so just some processing, nothing very profound about it. You can write Einstein equations like this. There should be a G factor here. You can write it like this in the form notation, or you can come from there to the now standard form that we have seen. So nothing great about it, just a formalism. And if you have Einstein gravity coupled to Dirac fields, you can do the same thing. First I had thought I'll do that tomorrow, but it is not much of a material and not very enlightening. So what I decided, I will talk about, that's a suggestion, you can suggest something else, the so-called Oppenheimer-Snyder 1939 paper showing how gravitational collapse of a star leads to the formation of a black hole. And those works have been generalized. Sometimes the gravitational collapse ends in what is known as a naked singularity. Sometimes the collapse stops before the horizon is forming. Those are called horizonless compact objects. So I could show the Oppenheimer-Snyder calculation. Thank you. I could show the Oppenheimer-Snyder calculation in one talk if you are okay. So, or anything else. Last lecture I want to reserve for Einstein-Cartan theory, unless you want something else. So please tell me, are you okay with gravitational collapse of stars? I'll work it out. Are you okay?
No, I was just wondering, in one of the presentation questions, one of them was given as a black hole is the only possibility for gravitational collapse.
Yes. Yeah, I had given that question. So I can demonstrate that with the simple model, the so-called Dust-Tolman-Bondi solution, that depending on what the density profile is, sometimes the collapse ends in a black hole, sometimes it ends in a naked singularity. So theory allows, in simple models, so the cosmic censorship hypothesis states that gravitational collapse will always end in black holes and never in naked singularities. But there is the rider to the hypothesis. Cosmic censorship hypothesis says that gravitational collapse of physically reasonable matter will never end in a naked singularity. So that's still unsolved. Some people say that sometimes collapse ends in singularity that is naked. And there's a deeper question. Singularities are not really physical things in nature. So general relativity definitely would have to be modified in the vicinity of singularities to overcome that singularity. So some of those things we can talk of tomorrow. Would you, that's what you are saying? Are you okay with that? Any others? Farus, you okay with that? So again, there will be some equations, but there will be some physical insight also. And the last lecture, Einstein-Cartan theory. Yeah? So I had one slide left, and let me show you that. So this I think Bhaswati did, no? Maxwell electrodynamics action principle in differential geometry notation.
Yes.
Action also.
No, not action.
Only the equation. So this so you can do that for the action also. Where would we? No, I just want to show you this last slide. Right. So I think I have missed out one slide here. Right. So A is the electromagnetic potential one form. So in Maxwell's electrodynamics, the potential is the connection. In GR, the connection is not the potential, it is the connection one form is like the forces. F equals dA is the field strength 2 form, J is the current 1 form, star is the Hodge dual operator. This is the Maxwell action. It's F square. It's F mu nu. And in the differential form notation, it's F wedge star F. This is the coupling of the vector potential to the current. So star J is the current 3 form. So compare this action with that for general relativity. The first term is the free electromagnetic field action. The second term represents coupling of the potential to an external current. Just have a look at this, try to remember F square. F square, A times J. Let's go back. What is gravity like? What is the action here? Right. It's not F square, you see. F is the curvature 2 form in electrodynamics, and the action is F square. Here the action is linear in the curvature 2 form. There it is quadratic in the curvature 2 form. And of course, leave out the matrix. This is very important. All along I've been talking of similarities and differences between gravitation and electrodynamics. So right here we are hit with a difference in the action principle. Linear in the curvature 2 form, quadratic in the curvature 2 form. Why that difference is there, I don't understand. We need to dig deeper what exactly is going on here. They are both using the same language of curvature and connection. The addition thing in GR, additional thing is the metric. But we saw both work in the fiber space. By the way, I should say one thing. All of this general relativity is happening really on the tangent space. The tangent space is an example of a fiber. Here the fiber is a vector tangent. The fiber is a tangent space. So it's a vector space, so it's called a vector bundle. In electrodynamics, the fiber is the Lie group U1, so it's called a principal bundle. But the language of fibers is common. You're doing parallel transport from one fiber to another. In electrodynamics, the parallel transport is done by the connection, which is the electromagnetic potential A. In GR, the parallel transport is done by the connection 1 form, which are like gammas. Okay? The connection in GR is like gammas. connection in electrodynamics is like the vector potential. So that language is common, but look at the structure of the action. It's very different. The equations also have some similarity, but the actions are different. Vary the action with respect to the potential one form. This variation, this is not the exterior variation with respect to delta A. Okay, so d delta A wedge star f, and again the other term, the variation, sorry, I made a mistake. D is the exterior derivative, f is dA. So delta f is delta dA, and the delta and the d will move across each other, exterior derivative of delta, that is this term. Then the delta will act on f and f star, again that will turn out that those are boundary terms which will anyway, delete what I said. This is the variation of f, substitute that here, that looks like this. Okay, that is written in the last line. Right, integrate by parts discarding boundary terms. So d delta A wedge star f, basically you transfer the derivative from delta A to star f, and this is what the variation looks like. Put together the variation for the matter part. The matter part is delta A wedge star j. Basically, I want to remove the d from the first term. I want to have it proportional to delta A. So, do I integration by parts, there will be a boundary terms, and this d will come and sit on star f. That is what is happening here, right. The d has come and sat on star f. So, this is my total variation. For it to be 0 for arbitrary variations of A, this object has to vanish, and that vanishing, this object has to vanish, and that vanishing, that vanishing gives me that d star f is star j. These are the inhomogeneous Maxwell's equations with sources, two of the Maxwell's equations. This don't need the action principle. If f is dA, then d square vanishing, this gives me the two source free Maxwell's equation. So now we have completed our differential geometry program. We have written both Einstein equations as well as general relativity, the field equations as well as the action principle in the form of differential geometry, which is what we set out to do a few lectures again. So that part is complete now, and tomorrow we will talk about gravitational collapse, black holes, naked singularities, and last lecture on the Einstein-Cartan theory. And if tomorrow this gravitational collapse does not get over, we maybe continue it in the last lecture. We will see how it goes. So good to, nobody has talked about gravitational collapse yet, no? No, tutors also know. Okay, so I'll do that. Okay, thank you. Thank you very much for listening.